Okay, so we're going to go ahead and follow along with part 2 of vectors of the plane. Okay, so last time we talked about the unit vectors. We talked about the vector operation, the magnitude. We talked about unit vectors. So the special case of a unit vector is, again, is a vector that has a magnitude of 1. Okay. So if I wanted a vector that is only in the x direction and it has no y component, it would look like this. Okay. So a unit vector that looked like this would be what? Since it's a vector, okay, but it has no y component, so it would be 0. And this is going to be what? For it to be a magnitude of 1, this obviously has to be 1. And there's a special name for this, and this is called a vector I. We call this the book calls this the standard unit vector. So an I vector looks like this. Correspondingly, we have a y vector, and that's called the j vector. And obviously, it has no exponent, and it's only going to have y. So it's going to look like this, and we call this the j vector, and this is the vertical standard unit vector. Okay, and where does this come into play? This comes into play if I had a vector that was, again, 3 and 4. We call this v vector. I can now say this is the same as 3i plus 4j. In other words, I could take the x and go 3i and take the y component and pull that out and say j. So if you look at it, this looks like what? 3i is 1, 0 plus 4 times, which is plus, 4 times j, which is 0, 1. So this is what? 3, 0 plus 0, 4, which is basically 3 and 4. So I took this vector and I can now put it in this type of form. Okay? So that's a special type of unit vector. Okay. So today we're going to go ahead and talk about direction angles. And what that is that now a vector, if I had a vector that looked like this, we would call this vector A. If I knew the theta there, I could now decompose or resolve this vector into 2 separate vectors. I can call it vector. I can decompose it into 2 vectors. One that looks like from here to here, so it's going to go like this, and then we're going to call a vector that goes up like a vertical vector that looks like this. So I can take this vector A, I can say vector A is going to be equal to the x component plus the y component. In other words, I can say that if this is a magnitude, so the book says what? The book says on page 460, the bottom part, it says resolving the vector into its components. And it resolves a vector A into the magnitude, which is the hypotenuse here, the magnitude cosine theta, because the magnitude of the cosine theta, and cosine theta right here, is that the green part, which is the x component, and the y component will be what? The magnitude of the hypotenuse times sine theta. Okay, so I've now taken this vector, one single vector, and put it into 2 different components. Okay, most of the time that I'm interested into the 2, I'm interested in the x component and the y component. Okay, most of the time that is. There is times that are not that way, and as a matter of fact, in example 9, we will talk about that. Okay? So this is how you decompose or resolve a vector. Go to example number 5 and see if we can do example number 5. Example number 5 says, find the components of vector v with a direction angle of 115 and a magnitude of 6. So I have a direction of, so I have 6 with a direction of 115, like that, right? 115 degrees. Okay, so it's basically this, right? So the vector is going to be 6 the magnitude times cosine 115, and the magnitude times the sine 115, and that is what the vector is going to look like. Okay, that's example number 5. Example number 6, find the direction angle of a vector. In example number 6, it gives us the points, and now we have to find the magnitude and the direction. So let's see if we can do that. Okay, example number 6. A, u is 3 and 2, where u vector is 3 and 2. So let's find the magnitude first. The magnitude is pretty simple. Square root of 3 squared plus 2 squared, square root of 13. So if I do this, I get what? Here is 3 and 2. Okay, so this guy here is square root of 13. I found that out. I just need to find what the theta here is, right? So the tangent of theta is what? Tangent theta is equal to what? Over 3, like that. So theta is going to be what? Theta is going to be the arctangent of 2 over 3. And as simple as that. So that's A. Now let's go to B. In B, we're going to do a V vector. In B, we have a V vector that is negative 2 and negative 5. Negative 2 and negative 5. So if I drew it, I get negative 2, negative 5, like that. So let's find the magnitude first. The magnitude is 4 plus 25, square root of 29, which means the magnitude here is square root of 29. I know this guy is negative 5. This guy is negative 2. So if I look at this angle, we'll call this angle theta. So if this angle is theta, what do I have for theta? I have tangent of theta is equal to what? 2 over 5. So the arctangent of 2 over 5, if I do that, I get what? I get, if I do that, I am going to get 41.8. 41.8 degrees. So this guy here is 41.8 degrees. So if I take this is 270, and I have to subtract that out. So the angle itself, the angle that I'm really looking for is from here to here. We'll call that alpha. So angle alpha is 270 minus 41.8, which is 228.2. Okay, so that's how I would find that. Okay. So now let's go and see if we do some applications. There are 3 separate applications here. So we'll do example number 7 first. Example number 7. Example number 7 says, a jet aircraft is flying on a bearing of 65 degrees at 500 miles per hour. Find the component form of the velocity of the airplane. Okay, so it's a bearing. Okay, now let's say navigation thing. And whenever we talk about navigation, we said the bearing always starts from the north. So we start from the north and we go 65 degrees like that. So 65 degrees is going to look like that, which means that this guy here is going to be 25 degrees. And this is actually what we really want here. And I have a magnitude of 500 miles per hour. 500 miles per hour. So the actual vector, in vector form, I'm going to get 500 cosine 25 degrees times 500 sine 25 degrees. And that would be in a component form, right? Component form, okay? So that's that. Now it's pretty simple. Example number 8. In example number 8, we have a plane that is flying from San Francisco, but it's flying into a wind. It has a wind. It has a wind that is 65 miles per hour with a bearing of 60 degrees. In other words, again, it's 65, but it's bearing of 60, so we go from here 60 degrees. So I'm going to get 30 degrees here, and this is 65. The magnitude is 65. Now the jet itself is going at 450 miles per hour. The problem is that if I go straight 450 miles per hour, the wind is going to push me off like that. And I don't want that to happen. I want to go directly east. So the resultant vector, when I add the two together, is going to be directly on the x-axis going east. So in other words, I have to compensate for this wind and go a little bit this way. Okay, let me redraw that. I have to go a little bit this way, like that. Okay? So I want to know what that theta is. How much do I have to go off 450 so that my resultant vector, when I take this vector and I move it down here, like such, the end point is going to go like that, so my resultant vector is going to look like this. So the resultant vector is going to go from here to here. Okay? So what's actually happening here? What's happening here is that this wind is trying to push the plane off, push it y to the y positively this way a little bit this way. Whereas if I go down that way, I'm going to compensate for that and end up going straight. In other words, the y component of this vector and the y component of this vector, the two are going to cancel out each other. In other words, the y vector here is going to go, the y component here is going to go the positive way, the y component here is going to go the negative way, and they're going to be equal in opposite directions to cancel out, so all I have is the x direction. So, this guy here is going to look like what? This guy here in component form looks like 65 cosine 30 degrees, 65 sine 30 degrees. Where here, this guy, the x component is 450 cosine theta, and then I'm going to have 450 sine theta. In other words, this y and this y are going to be the same. So I have to put those equal to each other and solve for theta. So I get 65 sine 30 degrees is equal to 450 sine that. Sine 30 is 1/2. So this is the same as 1/2. So what I get here, 1/2 of this is 32.5. So sine theta is equal to 32.5 divided by 450. Theta is going to be equal to the arc sine of 32.5 over 450. If I do that, I find that theta is equal to, where is it? 4.14. 4.14, okay? So the plane itself is going to, from a bearing standpoint, I'm going to start from here, 90 degrees, and then 4.14. So the bearing of the plane itself is 94.14. So the bearing is 94.14. And then it wants to know what? Determine what the ground speed is. The speed itself is from here to here, so I'm going to add this guy plus this guy. So the ground speed is going to be 65 cosine 30 plus 450 cosine 4.14. And that would be my total ground speed. If I do that, I'm going to get what? 505.12. There you go. And that was example number 8, I believe. Example number 8. Okay, so last but not least, let's do example number 9. Example number 9 is the one where we are now not going to decompose a vector into x's and y. We're going to do something else. So in number 9, example number 9, I have an incline like that, 20 degrees, and I have a box that is sitting up on here, and the box has a certain amount of weight. The weight is going down this way. Now this weight, okay, for those of you doing physics, people who have done physics knows that this is the reason why. What I really want to know is, what I'm really interested in is not, I'm interested in what's going down like that, right? I'm interested in decomposing this into this guy and this guy, all right? So in other words, this guy plus this guy, which is the same as that guy. This guy plus this guy is that, and that is the weight. Okay, so we could call this the weight. I don't know what it is, but I do know, so this is 20 degrees, that this guy here is 20 degrees also. Okay, so the box is being held in place by a force that is going equal and opposite in this direction by 30 pounds. So in other words, the weight, and this guy here, so this is what? Sine, the weight times sine 20, which is this guy here, is the same as that guy, which is 30, and that's what I'm trying to find out, okay? So it's going to actually look like that, because it's the magnitude of that. So that is equal to 30 divided by sine 20. Okay, and if I do that, I get what? I get 87.71. 87.71. Okay. In reality, what's happening is what? In reality, what's holding this box from falling down is the friction force that is coming, that is between the box and the incline itself, that is holding the box. And those of you who've done physics, we know that the friction force looks like that. Right? The friction force is a mu times the normal force. Normal force is a force that is perpendicular to the actual surface itself. Okay, so that's what's holding it. All right. Those of you that don't understand what I'm saying, you'll find out in physics. Okay, that's it.